Okay, just to make sure everyone is on the same page. What is the Z distribution?
It's a normal standard distribution.
Yep. Okay, that's very good. Basically, a normal standard distribution with mu, that is mean, is equal to 0. Okay. How to find this Z value? X minus mu by sigma. How to find the error value?
E equal to Z alpha into 2 and sigma square n.
Z alpha by 2 is only applicable when you are dealing in two-tail. Otherwise, you can just write alpha and get ahead with it.
Okay.
But yeah, if it is two-tailed, you should write alpha by 2.
Square.
Okay.
Yeah.
So interval estimate is, or interval ranges. Let's call interval estimate. So what is interval estimate?
It is m plus minus, right?
Sorry.
Interval mu plus minus, yeah.
Yeah. Okay, I think, sorry. So this will give you an idea how to calculate all of this interval estimate and everything. So what is confidence interval?
It's also called normal distribution.
Confidence interval? No.
Yeah.
Come on, confidence interval. Okay, so it is like represented as like 90% CI. If someone says 90% CI, that means 90% confidence interval. What does it mean?
Oh, yeah. Okay.
90% of the samples follows the.
Yeah, very good.
Yeah.
So if you determine interval estimate,
is the quality of the product, right?
yeah, it is kind of dependent, of course, because then basically what you can also mean is like your standard deviation might be very less, and that's a good thing usually.
Range of
No. So the range, and the point is the range that you say,
possible values.
not just possible values. We are worried about this range is okay. So remember, it's a Gaussian distribution, right? Problem is Gaussian goes from negative infinity till positive infinity. So you can technically never have 100% confidence interval, right? You will have to include all the outliers basically. So it is not possible. So the idea is this range is valid for how many samples, okay? Or if you take a good enough sample, still how many samples should fall under is within this range, okay? With what confidence you can tell me that this answer will be true, right? So that is what, so if it is there and if I say 90%, so I mean to say this range is only applicable for 90% of the samples or the 90% of the examples. 10% examples still might fall under or fall out of the acceptance region, okay? Okay, one second. Just read this, okay? Just read this once. Is it clear? What do we mean by confidence or confidence interval? Okay. Any questions you can
X
ask right
mean
now?
is it's a mu only, right?
Yeah, X mean, yeah,
Because mu plus or minus of
yeah, you are right. You are right. Basically, I say this or X mean or mu. Basically, we are referring to the same thing.
okay, understood.
Oh, okay, all right. It does pays off to remember few values of z-score. Not again, it's not possible to remember all of these. And just to make sure that you remember that this is for two-tail. So okay. So 50%, 80%, 90%, 95%, 99%. It does helps like remembering like five values of sine theta, or cos theta. Again, you don't have to remember all the values of sine theta, cos theta. You can use a calculator or a computer, or maybe even there are few charts for this. But remembering a few key values are like is very important. Okay. Okay. So we were dealing with sigma known cases right now. Okay. This is population. What if sigma or the population standard deviation is not known? Those will be called sigma unknown cases. Now, if there is sigma is unknown, you won't be able to apply z distribution. Okay, because z distribution takes this assumption that you do know the population parameter. Okay, because you can see in the error calculation itself. For two-tail, it is equation is like this. But unfortunately, we do not know this. Let's say if this is not given, then it would be slightly hard. But again, we can find some approximation to solve the problem. Okay. But these kind of set of problems are called sigma unknown problems. Okay. But again, another assumption is that data is still normally distributed. Okay. So even when I am gonna talk about t-test or t-distribution, again, that is based on the idea that it is normally distribution, normal distribution. So you cannot really get rid of normal distribution here. So if an estimate of population standard deviation cannot be developed prior to sampling, we use the sample standard deviation to estimate the actual sigma. So we are gonna use the sigma as, or let's call it as to estimate the, now again it's a estimate, so again you can be wrong with some measure as well, but this is what we are gonna do. We are gonna work with the sample standard deviation. This is called sigma unknown cases or standard deviation unknown case. Now in this case, the interval estimate for mu is based on t distribution. Okay. Now remember, still your assumption is population is normally distributed. Otherwise, you cannot apply t distribution. Okay. So what is t distribution exactly? Anyone heard about it so far? So t distribution, William Gauss, writing under the name of student, is basically the founder of t distribution. Okay. He developed t distribution while working on small scale materials and temperature experiments. So basically he was trying to kind of associate everyone's melting point and boiling point with just taking a very small sample. Now the problem is when he was doing all this work, uh, the boiling point or the melting point for all the materials were not known. He was just dealing with some samples and he was trying to estimate the overall boiling point and the melting point of the different materials that he had at hand. So now the problem you might understand, because there is no global reference, so you do not know the standard deviation. Okay, the population standard deviation. You are just working with the small sample that somehow you have procured. Now remember, t distribution is a family of similar probability distributions. A specific t distribution depends on a parameter known as degree of freedom, and basically it refers to number of independent pieces of information that goes into computation of S. Okay, t distribution with more degrees of freedom has less dispersion. Now you might be thinking, what does dispersion means? Okay, so let me show you with a figure. So you can see here, okay, and now you have to imagine, okay, so V is nothing but, this is called DOF or degree of freedom. All right, V is degree of freedom, and how it is calculated? V is mathematically n minus 1. Okay, so n is the number of samples. So as the idea is, as V approaches infinity, t distribution will become z distribution basically. Means V is equal to infinity, t distribution is practically z distribution itself. Otherwise, we are basically approximating z distribution using t distribution. Okay, so you do require more independent pieces or more degree of freedom to estimate it better. Okay, again, it's not possible to get that much degree of freedom or that many samples, but we will see what we can do with this information. Just going. Okay, so fundamentally, in a very simple idea, if I had to explain you, t-test or students t-test compares two averages, means, and tells you if they are different from each other and how much different they are. In other words, it lets you know that could the difference could have happened by chance or not. Okay, let's say you have a very simple idea, or let's take a idea of having a cold. Okay, and let's say you try some naturalistic remedy. Okay, your cold lasts couple of days. Okay, 1 or 2 days, that's it. Next time you have a cold, you buy over-the-counter pharmaceutical and cold lasts for a week. Now to understand what just happened with you, you try to survey your friends and they all tell you that their colds were of shorter duration, an average of 3 days, when they took the homeopathic remedy. Okay, what you really want to know is, are these results repeatable? Because you can understand, no, there is no global population that you have like surveyed, it is just few of your friends. So a t-test can tell you by comparing the mean of two groups and letting you know the probability of those results happening by chance. So basically you can compare different means and basically try to understand how much is this a chance, or like how much is the certainty that this will repeat actually. Okay, So many times to determine which is the which might be the best variable, or even in machine learning, we do apply t-test on various columns just to understand that something is not coming just by pure chance. There's a chance that this will repeat and this has some significance in the data set. Okay. Okay. So I want you to write down this error estimation. So now your error or interval estimate is x bar is nothing, it's just mu, and this is your error equation. Now this is t value providing an area of alpha by 2 because it's a upper tail distribution or t distribution with n minus degrees of freedom, and s is equal to sample standard deviation. Remember, this is the sample standard deviation because it's still a sigma unknown case. Now how to use this? So let's please write down this one and let's use this. Okay, here is the question. Please note down the question.
Excuse me, can you repeat again?
Like what? Which part exactly?
Like the equation signs mean, what is the use of that for what?
It's an interval estimate in case of sigma unknown. Okay.
Okay.
So this is mean, mu. This is the t-score, which I will tell you how to calculate. S is the sample standard deviation. N is the sample number or sample size. Clear?
Yes, now it's clear.
Okay.
Thank you.
Now, note down this question because let's try to solve it. So remember, there is no population standard deviation that is given. You have a 16 one-bedroom apartment within half mile of campus. So you're trying to kind of estimate off-campus housing, okay? So the sample mean is 750 per month and a sample standard deviation of $55. Now let us provide a 95% confidence interval of the mean rent per month of the population of one-bedroom efficiency apartments within half mile of a campus, okay? Now the assumption, again, remember, the assumption is it is normally distributed. So how will you calculate all this? So the maths is very simple. You want to get the interval estimate. So mu plus minus t, let's say alpha by 2 into s by root n. Now, almost all of the values are given. 750 plus minus, apart from t alpha by 2, of course, into s is 55. Okay. Now, how to calculate this one? Okay. So ready? So fundamentally, we have to look. Sorry.
Let us provide the 95% coefficient interval. So alpha will be the 0.95 by 2, right?
Yeah, no, not 0. Okay, we will come to that. No, it will be actually 0.05 by 2. Okay, so But the confidence interval is the acceptable limit, right? So let's say the middle 95%. So this area and this area is alpha by 2 and alpha by 2. Okay, basically Ci plus alpha should give you 1.
So Amritans, this is not a two-tail then.
How?
Am I correct or am I wrong?
No. How did you estimate that? It is not two-tail.
I think no. 95% is coefficient interval estimated is there. So alpha by 2 might be the 95% for each, I think.
No. Alpha is not 95 here, please. Alpha is 0.05.
1 minus alpha by a 1 minus alpha. Okay.
No, 1 minus Ci, not alpha would be 1 minus Ci. Okay, I will take this here. Okay, so alpha will be 1 minus Ci. So if Ci is 95% or 0.95, how much is that?
Okay, 0.05. Yeah.
Yeah, but it is like a range, right? You have to understand the question. So they have never said it should be only one tail. Range could be plus minus, right? Some average rent plus minus whatever your error is. So how it has to be a double tail unless the question really specifies it very clearly that no, only the upper area or the lower one you have to consider. Whatever with the understanding of the question we have, it is clearly a double tail question basically. Okay. Now the problem is how would you find this t-score? So again, there are calculators as well as t-tables. So let me show you how to calculate a t-table. How to get the values from t-table. Okay. So I think these will be good. I want a bigger one. Yeah. So open image in new tab. Okay, good enough. Okay, how to find it, guys? Okay. So it's a simple idea. First, you need to know degree of freedom. What is degree of freedom here? So your DF is? What is M?
16.
So DF is?
15.
Very good. Now you have to read it is one tail or two tail, okay? Okay. You have to read this, that is it one tail or two tail. So we will have to assume because the question doesn't specifically specifies all this stuff. So we have to assume it is a two tail problem, okay? Now for two tail, we have to find 0.025, okay? For two tail, because in basically 0.05 means CI as 95% or confidence is 95%. Okay. So again, for this one, you have to start looking down till basically take both of these arrows. So what do I get? Okay, one thing I want to show you first. See, if as it goes bigger, as the DOF, as I said, DOF becomes bigger, it becomes closer to Z distribution. So what it means is at some infinity, see at 1000 it is 1.962. If you remember, for 95% it is 1.96. But this is at infinity, and even at 1000 we have reached like 1.96. Even while taking more than 80 examples, so 80 examples, you are at 1.99. So it is not very far off if you really think about it, because at infinity your t tail will t distribution will be exactly equal to Z distribution. Okay, that's why these values are given here. But simple idea, if I had to explain you, if you had to consider this value very carefully, you can imagine at positive infinity, let's say Z, this is exactly equal. Okay, but even till 1000 we are not really very far off. Even while we are taking 60 or 80 examples, we are not very far off from the actual value of z distribution. So t distribution is a kind of estimate when you cannot work with z distribution because you don't have the global standard or population standard deviation because you have taken a very small sample, and of course there would be error in estimation. So we have to work with this value 2.131. So can someone tell me the a confidence interval right now? What is the confidence interval?
%95.
And the range is? Actually, 95% should be just said, I think, confidence. If I said something wrong, please pardon me. That would be just confidence. Confidence interval would be the range, mu plus minus error. So what is the error? Sorry, what is the confidence interval exactly for this? So you have all the data.
750 plus or minus 29.3.
Sorry, how much? How much?
750.
Ranges.
Error is 29.3.
So ranges
750 plus.
from where to where? Can anyone tell me?
Is it 55 plus 2.131?
Sorry, where is this 55 came from?
It's a standard mu, right?
So mu is, this is standard F.
Mu is, yeah, I just confused you.
So T is 2.131. Okay, N2S is 55 by. So tell me from where to where the range is?
720.698.
How much? How much? One sec. One sec. So let me also do this calculation once in parallel. 131 into 55 divided by 4. That comes to 29.3. Right?
Yeah.
So
720.7 to 779.3.
720.27.
779.
779.3.
You can estimate with this idea with 95% lesser confidence that the campus housing or one bedroom apartment, even with this very small sample, that one bedroom apartment is from $720 to some $780 per month. Okay, you can say almost 95% of the samples or 95% of the houses will be very much in this range. So it's a nifty piece of information, really, if you think about it, that even with a small sample you could determine something. Of course, now you might realize with this table that the smaller the sample size, see, if the sample size is really small, your estimations are going to be very wrong, right?
Okay.
Are you getting that point? Because look, if you have some infinity points, it will be exactly equal to z distribution, but we don't, of course. But see, it should have been, let's say, 1.96. But as you go smaller, let's say here, see here, 1 for 1 or 2, 3 points, how wrong you are. It's like quite a magnitude of it is wrong. Okay, only after once you kind of enter this domain, like usually a good thumb rule is to use anything beyond 30. So try to get more than 30 samples at least. Okay, usually, because then these values are like approximately very close. I usually tell people to go for 60 or 80 at least minimum. Okay, because then the values are like really very close to a z distribution estimate itself. So if you take like very small values, it is not going to work out, or the difference is going to be so much, the range will be too big. Okay, so at least have a decent sample size, like close to 60, 80, okay, or even maybe 100 if it is possible. So now someone might ask, like, but how to determine the sample size, right? So I'm saying all this, but how to determine the sample size itself? This is a big question. So now try to remember the equation of z distribution. So again, I might have told you there's not one idea, but there are certain thumb rules, and there is of course some mathematics that we can do. So if E is the desired margin of error, so first you need to tell me how much error are you willing to tolerate. Okay. So in case of Z distribution, when let's say the sigma is known, what would be value of let's say sample, optimal value, let's say. So the maths is really simple. You just need to switch around some variables. Okay. So this is the equation. This is sigma known case. Okay, guys. So n would be, just switch the numbers.
Sir, how to know whether it is a one tail or two tail?
Yeah, that will come from practice, and you will have to read the question very carefully. And in hypothesis testing, I will try to explain this problem, that how to exactly know is it one tail, two tail. Okay, but it comes with practice. It's not that easy to always identify. So only by practice, only by seeing more and more questions, you will know it is a one tail or two tail problem.
Okay.
So wherever you see alpha by 2, to immediately understand it's a two tail. Okay, the equations at least.
Amritan, to understand the difference between the Z score and the T score, is it only the sample sizes which
No,
makes?
No. Is sigma known or sigma unknown case? Do
Uh,
you know the population standard deviation or not? That's the defining property. If I know sigma known, I will always use this distribution because it is the exact estimate of a normal distribution. If
agree.
I don't know, then for s is sample standard deviation, then only I should look into t distribution.
Then what is the importance of getting the n here when sigma known? Then directly I can jump into the Z
No,
score
but
test.
no, hold on. Without knowing the proper optimal n, don't you think your error value will be also wrong?
Absolutely correct. You are very true. What is the range of n that I have to consider for the if this standard deviation is known? And
There is no range. Okay, so your problem has to define how much error you are willing to tolerate.
okay.
Okay, you should be like, okay, I want the let's say this apartment estimation, but within the range of $10, miss within plus minus $10. Now tell me how many samples you require. Get the idea? So it has
Got
to be
it.
defined in a different way. Like someone has to ask, or someone has to come and ask that, okay, I am already willing to tolerate the range or difference of 5 units or 5 ml. Now you have the Z value already, confidence is already given. Now tell me how many samples you require to solve the problem.
Okay.
So remember the Coca-Cola example?
Yeah.
So in Coca-Cola example, now I can say, okay, I'm willing to tolerate plus minus 10 ml, okay? And I am looking for, let's say 99% CI because it's a food industry, right? So they need to keep their standards very high. So now tell me how many bottles I should collect to actually do the maths.
Yeah, agree.
So maybe that question might be falling under single tail because lower is the problem, upper is not a problem really. So over there, let's say you have Coca-Cola tells you the standard deviation of the whole population and you are willing to tolerate, let's say, now you have to be careful with the sign, but let's say if it is 0. Because it's an ml, okay, whatever it is. Okay, now it depends like what these two signs were in. Okay, fine, whatever, you can find the minimal number of n that it requires to solve the problem. If you take anything less, your error will be actually much more, which is very evident from this equation. Because if you take a smaller number of n, this root will be even smaller and the whole term will become bigger. But you also do not want to take like a very large n because again, mathematical truth can be estimated with the optimal number of n. And in a lot of ways, you will see the thumb rule, which people say is adequate sample size. So I simply tell them if you have no information, just go by root of n. Okay. Root of n, oh sorry, actually, sorry, my bad. N should be root of capital N. Okay, but that's like a thumb rule. It doesn't always work. So when you have been given like Z confidence interval and everything, it is better to estimate it like this because this will be more clear. So just to make sure that you understand this problem. Now necessary sample size equation requires a value for the population standard deviation sigma. If sigma is unknown, a preliminary or planning value of sigma can be used in equation. You can use the estimate of population standard deviation from a previous study, or you can do a pilot study to find a preliminary, some standard deviation from that study, or you might have to use a judgment or a best guess. So you might have to talk to some domain expert or some kind of subject matter expert to figure out what should be the best value to start a work with. Okay. So, okay, solve this problem now. So I might actually have to go to this problem. Okay, so they are basically asking how large a sample size is needed to meet the required precision. So they want this 0.95. So you understand your confidence is 0.95%, but they are looking for sampling error of $500 or less. So this is what I was talking about. It is given in the question, or at least someone has to specify this. How much error are you willing to tolerate?
कौन है साची है किथे है
Hello.
रवि भैया
Hello.
I'm sorry.
Okay. Okay. So how would you calculate this? I think you will require some information. So again, this is the same problem. Now remember, you just do not know the size, n basically, but rest of the information remains the same. The sample mean income and the population standard deviation is given. So can you calculate the number n? How will you find the n? Sorry. Value of n is everything is squared here.
226.
226. Are you sure about the maths? Because remember, you have to do for 95% confidence interval. So what is the z value or z alpha by 2 value over there?
1.6.
No, no.
Okay, sorry.
You have to remember these values, guys. This is what I'm talking about, okay? So now can someone tell me what is the n?
Approximately 312.
How much? Sorry, can you repeat?
312.
What was the exact value? Can you tell me?
Exact 1 minute.
Hmm.
311.1696.
311 point.
1696.
Okay, good, very good. So now the problem is, if you're trying to determine sample size, you cannot have decimals, okay? So basically n has to be greater than or equal to 312. Why greater than?
Because it's already greater than 311, so we can't consider 311.
Yeah, or reason is this. You are just not dealing with 500. Basically, your sign was just not error should be. It was like this. Should be less than equal to $500. So you were trying to solve for equality. That's a good thing, but there is an inequality as well here in the equation, because it could be 500 less, right? So I should tell the manager that, sir, I would require more than either 312 is good or more than 312 samples if you want the error range to be even smaller than 500. Get the idea? Is everyone getting the same answer or not? Okay, let me ask you another question. Can I do it with the t distribution? Yes or no? Same thing. Basically, if I wanted to calculate the optimal number with this kind of variable switching, can I do the same with t distribution? Yes or no?
I think yes,
Sorry.
we can do that. I think.
Okay, how will you do that? You want to see the equation?
Yes.
One second. So how will you solve this problem?
All the 95% of the confidence interval. Directly, you can take this t value for the two-tail test for the 5% of the error margin and compute the n value.
But T is also dependent on?
Mean standard deviation.
No.
Okay.
Degree of freedom here.
Now you see the problem. There cannot be two variables in a single equation to solve. Look, error, as you understand, is right now T alpha by 2 into S by under root n. So you were just thinking I have to solve for under root n. No, the problem is T. Because T is just not dependent on confidence, T value is also dependent on the n minus 1. So there are two variables in the same equation. So you can't solve for two variables.
Correct. Clear.
So because if anyone has doubt, you can look in the chart and you can realize this df is nothing, it is n minus 1. So because T value will change based on the samples. So rough estimation, as I said, anything greater than 30 or 60 is a good idea. Based on our current estimate or the rough estimation that we see how far away or how close enough we can get to an actual Z distribution. Okay, but you cannot exactly estimate error. It's not possible because the T value also changes with the number of samples.
Britank, if you find the T distribution here also, so it will be not coincident with the J distribution as the sample size is very small, right?
So I think I showed you this picture, right?
Yes.
Imagine this black one is perfect normal or Z distribution. And the T distribution is slowly becoming like Z distribution when you increase the sample size.
Yeah, correct. As per the equations.
Yeah. So the idea is it is kind of a bell curve and it will exactly become a normal distribution when it becomes close to infinity, but that's never going to happen. I'm not going to get all the samples on the planet Earth. Otherwise, I will basically get the whole population, right? So so the idea is as you go closer, when your degree of freedom increases, so the idea is when your sample size is anywhere, according to me, is greater than 60 or something, it is approximately very close to a Z distribution.
That is one point, and it is always depend when you do the T distribution. It is always to depend upon the n minus 1 first.
Exactly. So in this one, there are two. If you wanted to solve for n, you can't because T itself is dependent on n.
Okay. So how we do it, the J distribution? I mean, n equal to.
Because Z distribution is not dependent on.
Yes, yeah, correct.
Good one.
I'm coming back.
So Z distribution is not really dependent on. Sorry, because Z
Not
distribution
dependent upon the
values
sample
are
size.
fixed. You see, there is no dependency on n. These are fixed values.
Yeah.
So I could just simply swap them that we have done here, and that works because Z value, Z alpha by 2, doesn't changes by n. It remains the same. So there was no problem while swapping them and kind of converting them to the another equation.
Okay. Two equations. So for the G distribution, there is a two equation, E and N, but no T is only T.
Yeah, just remember the T value, the T alpha by 2 value will change based on n, and you are trying to estimate n. So you cannot have two variables in the same equation in a single equation and solve for both of them.
Okay, thank you.
Okay, now people might be wondering what's the use of all this, like why we are doing all this. Now there is a bigger idea basically, and that's called basically hypothesis testing. And that is where we are basically, that would be technically our last major topic. So what is a hypothesis? Anyone knows about this?
Assumption for study.
Assumption for study. Okay. Any other example? Or assumption might not be a very good word here. What is this hypothesis? Okay, what is hypothesis in science? Can anyone tell me?
Hypothesis is like a theorem or theory.
Sorry,
Testing
again.
for different cases. Testing.
Testing for different cases. Simple. In simple words, what would be hypothesis? Just that's all I want to
A
know.
theory or theorem.
Theory or theorem. Okay, theory is a good one, but not a complete one. So hypothesis can be simply defined as some kind of a mathematical equation might not be the exact word, although we can say mathematical equation, but some kind of a mathematical truth you are looking for. Okay, or you basically you start with this one. Okay, you make an equation. Let's say that underlying function is x plus y is equal to z. Now basically you try to prove that it is true or not. Okay, so it's kind of a mathematical equation or mathematical truth you want to be true, and you start experimentations after this. Okay, so hypothesis testing is like a very big part of data science. The idea is, and you will find this problem again and again while testing the modules, that how do you know model 1 is better than model 2? And I will give you some example. So how do you know this? Which one is better? It's very tough to determine. You might feel this is a trivial problem, but believe me, it's nowhere trivial. Okay, it is actually a very hard problem to solve, and we cannot ever say that with certainty. Okay. So basically this is where we have to start a new chapter basically. And wait, let me open the folder. Okay. So let's start hypothesis testing. Okay. Hypothesis testing can be used to determine whether a statement about the value of a population parameter should or should not be rejected. Okay. So fundamentally some kind of equation that you are deriving, should it be accepted or not? Now there are different terms, and let me explain each term as it is first, because it will get very confusing if I don't. So there is something called null hypothesis. Do you understand what null hypothesis means?
I think zero value.
It looks like that, but no, you cannot take a literal meaning here.
The hypothesis which says false for the another hypothesis which was mathematically proven.
Okay, the idea might be there, you might be on a correct path, but null hypothesis simply means default hypothesis. Is some kind of a default or a base assumption that you accept to be true till some alternative or research hypothesis comes, or research hypothesis is thrown around and basically you have to make sure that which one is correct. Okay, now it is very hard. First of all, let me tell you, it's not an easy discussion to have. Okay, so null hypothesis simply means default hypothesis which was already existing. Okay, so null hypothesis denoted by H naught. So whenever you write null hypothesis, the usual sign is H naught, and for alternative hypothesis or research we write HA. Is basically a tentative assumption about a population parameter. It could be about like mu or about standard dev, some kind of population parameter. Okay, so basically the idea is very simple. The hypothesis testing procedure uses data from a sample to test two competing statements. Now HA H naught and HA should be mathematically opposite. Means if H naught is true, HA cannot be true. If HA is true, then H naught cannot be true. So they have to be mathematically opposite. Okay. Okay. Now it is not always gonna be obvious, and I think this was questioned by some people, and even I said at that exact moment, it's not always easy to basically identify this, guys. Even however hard we try, it's not that easy. And you have to take very special care to structure the hypothesis in a way that test conclusion provides the information that researcher wants. Okay, and knowing the context in this situation is equally important. And sometimes you can identify the alternative hypothesis first, and sometimes identifying the null hypothesis is easier. And remember, correct hypothesis formulation will take a lot of practice. It's not that easy to do it. Okay, let's take some examples. Okay, let's take an example that a new teaching method is developed that is believed to be better than the current method. Alternative hypothesis is what? The new teaching method is better. Cool, very easy to find. Null hypothesis, the new method is no better than old method. Now it's very hard to disprove, isn't it? Basically, null hypothesis is that even the new technique is more or less same. Alternative is no, new teaching method is better. Now, how would you prove this? Or how would you disprove the null hypothesis so that we can accept alternative hypothesis for now? Any idea?
Maybe by testing.
Sorry?
By testing.
Okay, by testing. Good, good. And how would you test? How would you test?
So
Well, I don't know. Just like, for example, in marketing, there is also A and B testing. Yeah, so
Yes,
I
A and
assume
B
that it
testing.
is. I assume that it's
Yeah,
similar
A and B
approach.
testing is that same, right? There is, let's say, model A and then there is a model B.
Yeah.
So how do you know which model is better?
Well, usually, they test, let's say, if it's, let's say, creative artworks, they usually test it by showing to other people, and then, by frequency, like, which model is frequently accepted in the other model, and then based on that, they decide.
Very
But
good.
in this case, also, the sample size is unknown. Like, sometimes they work with their available people, and sometimes they have enough people. So it's
Yeah, of course, sample
this way.
size is of course a problem, and but you might have realized it's not that easy a task to even do A and B testing. It's pretty tough, But anything wrong sample size, different kind of participation can ruin the whole study very fast. Okay, so I will of course tell you the tools how to solve this problem, but remember, it's not easy. Okay. There's no one fixed way to solve all the problems. There are different ways to solve the problems, okay? But A and B testing is like one of the very good examples. And same again, you can have different ones. A new Salesforce bonus plan is developed in an attempt to increase sales. So you alternative hypothesis is the new bonus plan increases sales. Null is new bonus plan does not increase sales. Means it is as same as the previous one, which was already in the place. Okay. And again, you can come up with different kind of. So basically you can start with an assumption or a mathematical belief that value of population parameter is true, whatever it is, mu or standard deviation or something else. We then use a hypothesis test to challenge the assumption and determine if there is statistical evidence to conclude that the assumption is incorrect. But in these situations, first you should know what is the null hypothesis, isn't it? Otherwise, what are you really challenging here? Okay, so this you might relate very clearly immediately. So label on a soft drink bottle states that it contains 67.6 fluid ounces. Okay. So null hypothesis is, what would be the null hypothesis here, guys?
There is no differentiation on that. It is correct.
No. So what would be a null hypothesis? You will say it is correct, right? Most of the days you accept like what is written on the bottles or the packets, right?
Yeah.
So let's say, because, okay, so if someone gives me, let's say 750 ml of cold drink or even more, I will be happy, right? So the null hypothesis is mu is, the mean is more than, if you do not understand fluid ounces, you can imagine the question in 750 ml. Mu is greater than or equal to 750 ml, right? That would be a null hypothesis. What is the alternative hypothesis here?
If you get the less one.
Exactly. And these two, remember, how do I say this? These two have to be mathematically opposite. That's a requirement to work here.
Okay.
Okay, that's a very thorough requirement. Okay. Now, so let's define things. Someone actually asked me, how do you know if something is one-tailed or two-tailed? And I told, let the hypothesis chapter start. Okay, so once you can define them in mathematical terms, then it is actually easier to tell all of this. Okay, and try to remember this slide because this will be very helpful. Now, let's say in general hypothesis test about a value of population mean mu must take one of the following three forms. H naught, mu is greater than equal to mu naught. Okay, mu is some mu that you have tested for. Mu naught is the default, so mu naught is default mean, which let's say has been accepted that it is correct. That let's say 750 ml. That yeah, you know it is correct or it has been assumed to be correct. And you are saying no, actual mu is less than the mu naught that you are claiming. So when you are claiming lesser than, this is also one tail example, but this is about a lower tail problem. Why? Because let's assume filling property. So what you are saying is, with some confidence of course, that if the filling is a Gaussian process, let's say this is where 750 ml is mean, then with some confidence interval, so you are saying no, my mu is falling here in the lower regions, not in the upper one. So it's a one tail problem because anything upper is equally fine for me. Anything lower is the problem. So this is one tail problem, but this is of lower side. So this is one tail, but of lower tail problem. I would like you to write it out, okay, all three. It will be really helpful in the future as well. Now explain me the other one, how does that work?
Can you please explain one more time?
Can you explain the next one?
No, one more time.
So tested one is less than to that mu of 0, which is 750 ml. So it'll be come to the plus positive side of the thing.
Yeah, so basically you can take, let's say, some other example. Okay, if there is a precision tool or there is something that needs to be of 5 centimeter, okay, it can be slightly less, but it cannot be greater. Let's say if that is the criteria over there. So you are assuming the tool would be exactly 5 centimeter or slightly less. That's the default. But you say no, the tool has been not manufactured properly and it is actually greater than 5 centimeter in length. That is again a one-tailed example because only lower doesn't matter. Upper is the thing that really matters to you, that it cannot be greater than 5 centimeters, otherwise it would not fit inside. Okay. So that's one example for one tail, but it's upper tail problem. What about two-tailed?
Two-tailed might be it will be same the value what you tested and what does the default mean?
Default, or you can play it like this. Okay, You can say there is a medicine, okay? Now in medicine, both are bad. You cannot go beyond it. So let's say there is something inside. So you are claiming it is 500 mg, okay? All right. Now you have to understand medicine has to be very clear. So you say no, let's say 500 mg is here, and you design your, you draw your Gaussian here. Assume that this is also a Gaussian process, okay? So with some confidence, you can say that medicine, the range of medicine, whatever is filled, should be in this one. But now anything exceeding the medicine value upper side, if it is too much, then it also can be a problem. If it is too less, then also it could be a problem. Those problems are called two-tail problems. And with the mathematical science, you can understand which tail it is. If you have any doubt, please ask me right now.
Yes, can you please explain the last one, two-tail?
Okay, so like, okay, you understand when you take these tablets, there is this mg value written over there, milligrams.
Yes.
What does this mean really? You understand that?
On average?
On average, very good. So if I give you a capsule, and let's say if it has to have some drug or some chemical, let's say it is 500 mg. So at 500 mg is a very strong one, okay? Usually for most medication, if someone is giving you a 500 mg, it is like a strong medication. Let's say I give you 500 milligrams, okay? So what are you really expecting? That it should be equal to 500 mg with some plus minus, because there would be some error. Maybe 1 or 2 milligrams is fine, right?
Yes.
But if it is 515 mg, it might be dangerous to you. Okay, it might cause overreaction in your body. But equally, it cannot also be lower because then you are frauding people. You are claiming it has 500 mg of this chemical, but it doesn't. So the potency of the medicine is very less. So those kind of problems are two-tailed, where upper and lower both have to be checked. Means it cannot exceed the upper range as well as the lower range. So that would be a two-tailed example. Did you get it? Or you can take some other examples as well, no doubt. But
it's like when it comes to effect of something, yeah? If something depends on something.
See the mathematical science in all three. Check the mathematical science, you might understand that basically two-tailed would be like you would be aiming for the middle or the exact point, and anything which is not there or within that acceptable range in both upper and lower tail is not allowed. So those problems would be called two-tailed problems.
So in the two-tail, yeah, so how much is allowed, like, you know?
Yeah, that will depend on question. You cannot tell beforehand. That will definitely depend on the question. So we will look on the question problem. Okay. Remember, the correct formulation is very important. Okay, please note down this question. You have to solve this one actually. So operating in a multiple hospital system with approximately 20 mobile medical units, the service goal is to respond medical emergencies with mean time of 12 minutes or less. The Director of Medical Services wants to formulate a hypothesis test that could use a sample of emergency response time to determine whether or not 12 minutes or less is being achieved. So can you tell me which kind of tail problem it is? One tail, two tail. If one tail, then is it a lower one or the upper one?
The lower one tail.
How?
Because it should be less than your, it cannot exceed that more, and it should be 1 by degree.
Okay, now you have to be slightly careful here, okay? Slightly careful. You want, okay, so what is the one of the major aims of hypothesis testing? To disprove null hypothesis. So remember, what are you trying to find is, let's say 12 minutes is your mean, okay? Now with some confidence interval that we will provide later, you know there is some upper limit, okay? Now anything underneath or anything beyond this is totally okay, right? So this green shaded region is okay. But when it has to be rejected, when let's say your new mu falls in the outside of this region. So does it look like a lower tail problem or an upper tail problem?
Upper one, right?
Yeah, it's upper tail problem. Lower is fine, right? If it is taking 12 minutes or less, why would I care? Problem is more than 12 minutes, and by how much factor you are going it wrong. So the upper part is the serious problem. Okay. So this is one tail problem, no doubt, but it's an upper tail problem, not a lower tail problem. So if I say, or if I already tell you that, yeah, it is a kind of upper tail problem, how would you, listen to the question very carefully. How would you define the problem, first of all? Miss, you have to come up with the null hypothesis. So you have to come up with a clear-cut mathematical definitions of, or mathematical assumptions of null hypothesis, as well as the alternative hypothesis. So what is your null hypothesis here?
12 minutes or less, right?
So how would you write it? So you will say mu naught, or mu is less than equal to mu naught. Mu naught is okay. So this will be called H naught. What is your HA? See, HA and H naught right now are mathematically opposite of each other. Yes or no?
Oh, one side, I think.
Sorry, I did not get. What did you just say?
For one tail, it's opposite, but when it comes to the two tail, it will be same, right?
No, but we are not dealing in two tail. It's definitely upper tail problem.
Okay.
Look. If an ambulance reaches faster at your home, why would you care? Why would you complain about that?
Correct.
Only thing is, if you say the ambulance should reach within your home within 12 minutes or 15 minutes, you are depending, like your life might depend on it, right? So if
clear picture, sorry, tell me.
Sorry. So if ambulance reaches to your home within 12 minutes or less, that's a good thing, right? The problem is it true or not? Maybe, okay, let's say this estimate was made 5 years ago, okay? That yes, our ambulances reach anyone's home in 12 minutes or less. Now the problem is, let's say the traffic increased because more people have bought cars, so more cars, vehicles are on the street, right? So it might be actually taking more time right now to reach anywhere. But no one checked the data for let's say last 5 years. So a new director has come and now he wants to make sure about this part, that we are still doing this 12 minutes or less of thing. So how do you know you are doing this 12 minutes or less or no? Because again, if you just take one example, that doesn't prove anything. A sample size of 20. So let's say if you have a sample size of 20, now you want to figure out does my null hypothesis still holds true or not? So first what you need to do is you need to define the problem variable and you need to write it out properly. So the upper one is null hypothesis, the lower one is the alternative hypothesis. Is it clear? Sorry.
Yes.
Okay. Okay, first let me explain the actual problem here. Now, it might be very easy. You might be feeling that, oh yeah, it is very easy to solve, but it's actually not. There is a serious problem. Okay, because hypothesis tests are based on sample data, remember, not on population. It is only based on sample data. There must be errors in calculation, right? You have seen this. You have tried to sample different samples and you could see that it is different from the actual mean of the population. Am I right? Yes or no, guys? I want to hear that. So remember that Python exercise that you did? You took like 1 million numbers. And then what did you do?
Took different samples ranging from 100,000 to 10,000 and
yeah, very good. You took like different samples and you saw when you take small samples, the difference between the sample mean and the actual mean is too much. Okay. Now, of course, sample size is also something to control about. So if you do this mistake, and let me explain this mistake very well. This is called type 1 error. A type 1 error is rejecting H0 when it is true. That you are rejecting null hypothesis based on sample data when in fact is true. Means on if you would have taken the whole population, you would have found, let's say, null hypothesis is true. But maybe now you might see the problem that you can take a very small sample and you might be rejecting null hypothesis. If you do this kind of mistake, this is called a type 1 error.
So it's basically based on the sample size, yeah?
Yes, sample size or level of significance could another be problem, right? What is this level of significance problem? So alpha is called level of significance, okay? That alpha, remember? So the idea is, if you remember this very clearly, and if I have to draw this properly, even if you take Z distribution, okay? Based on alpha, do you remember the range actually increases? Based on alpha, the range will increase or decrease, right? Okay, what is the error value, guys, in G distribution? Come on, anyone? Let's say the sample size is fixed and we know the population standard deviation. But you see, by increasing alpha, okay, we can increase the error, and of course we can affect the range itself because this is what range is, right? Okay, tell me, if you take something like two-tail problem, alpha by 2. So let's say if you take alpha as 0.5, means only 50% confidence. The range would be very small, right? Maybe this much range is only allowed. So by definition of 50%, or the way we understand the confidence interval, we already know only 50% of intervals would contain this mean. So 50, half of times, one time will be true and the next time will be false. So it is so easy to reject any null hypothesis if you like take like 50% confidence. What about if you took somehow, let's say 100% confidence then? Although it can't happen, of course you cannot actually achieve this, but then you cannot ever reject null hypothesis because basically it is encapsulating all the whole range from negative infinity to positive infinity. So by controlling so by controlling the range, and the alpha is called level of significance, you can control this one, and basically you can do this testing correctly. Okay,
Can you
so
explain again, sir?
sorry,
Please explain again.
okay, how is interval estimated? Confidence interval.
Mu plus minus.
Yeah.
Right,
What is
error.
the error, and how the error is calculated?
With the formula that you gave, that.
Yes. Can you tell me the formula?
That's alpha divided by 2 if it's two-tail, and
Yeah.
then
Standard
standard dev divided by square n, right? Under root of
very
n.
good, very good. Now, do you remember do you remember a generic pattern? When we take a less confidence, let's say 50%, what is the Z value usually?
50%.
I will actually I should let's see if that is open already, just to refer so that you remember all of this stuff. Imagine in 50% your range would be 674 into whatever the value of sigma by root n is. This is true for 50%. For 80% confidence, your range is 1.282 into whatever, because this is fixed. Do you see that the range is actually increasing? It is 90%. For 95%, it is 1.96 into sorry, this is 99, right? Okay. Do you see that the range is increasing, yes or no?
Yes.
Yes.
This is what I'm trying to tell you. If you take a very small range, then you can reject anything, right? May say even a small margin of error, you are like, no, not reject the previous one. But then you have already taken like 50%. 50% says what? That only 50% of the intervals would actually contain the mean. So for next 50% or the rest of the 50%, so it is like 1/2 approach. So in one approach, I might be correct. In the other one, I will be completely wrong. So that is not a good value. Now you cannot also take like close to 100 because then it can encapsulate too much range. Okay, it would be such a big range that anything gets accepted. So the idea is there is usually 90-95% are actually a very good parameter to conduct these experiments. All right.
So just for me to understand, yeah, just to confirm. So in the case of Coca-Cola, yeah. So if it has very high confidence, yeah, I mean close to 100, it will have problem because
Yeah, then
if it
basically what you,
indicates,
yeah,
yeah,
basically you are saying that because the range will become pretty big, you are saying that yeah, it could be 750 ml and it can also be 700 ml because
yeah.
the range would be too big.
Yeah, I understood the concept, but just to remember for later on. Yes,
Yeah.
so in case of Coca-Cola, when it is close to 100, yeah, it will be problem because it's claiming that in most of the cases, like
No, all cases.
100, in
The
all
moment
cases, yeah, it's
because you
correct,
are
yeah,
taking
but
negative infinity over there as well. If you try to cover all the 100% in a Gaussian, you are working from negative infinity to positive infinity, so everything is included. So you cannot reject anything over there. But if you take a very small confidence interval like 50 or even lower than 50, then it is very easy to reject it. But the problem is, remember, you are working on a sample, not on the population. So it is very easy to make a type 1 or type 2 error. Now, what is the type 2 error? It is accepting H naught when it is false. Like what it is saying is, you accept H naught null hypothesis when actually it is false. Maybe it has been wrongly computed or over the time it should have changed, but we did not. So there are type 1 or type 2 errors, and let me just show you in this grid. I hope hopefully this makes more sense. So with the given problem, so population condition is the true condition and conclusion is your conclusion. Okay. Now remember, if H naught is true, null hypothesis, and you also accept H naught, you conclude that mu is less than equal to 12, then it's a correct decision. That's what you want. But let's say H naught is true, but you reject H naught based on your test. That is called type 1 error. Let's say for the actual population, H naught is actually false. Okay, it is not servicing in 12 minutes or less, and you accept H naught. Then you have just caused a type 2 error. If H naught is actually false and you also reject H naught, then it's a correct decision. So you want to be in the green boxes, not in the red ones. Do you understand what just happened here?
Yeah.
Okay, very good. Okay. This is the final concept I will try to touch today, and we can maybe take it rest of them to the next class. Now, first you need to know what is a p-value. Okay, p-value is, in all honesty, is just probability value. Okay, guys, there is nothing very fancy about it. Okay, the idea is very simple. P-value is less than or equal to level of significance alpha, the value of the test statistic reason, the rejection reason. But let me first explain what p-value really is, because this is where things get tricky for a lot of people. Okay, in a PDF, probability density functions such as a Gaussian, if we were to integrate from some region to some region, let's say if I integrate from here to here, negative infinity till let's say the mean, what is the value we will get?
1/2.
Very good. Gaussian. So if you integrate 1 by 2, perfect. Now, if I tell you basically this area calculation, you understand the integration is just area, right? This area is the P or probability actually. This area is probability and the P value happens to be here as 0.5. The total p-value means if you integrate from negative infinity till positive infinity, your total p-value will come as, but we are not aiming for that, okay? P-value 1 is not something that we are really interested in. Now, what is alpha? What is alpha exactly? It's basically called level of significance. In this Gaussian, how would you represent alpha?
Percentage of confidence, right?
Percentage of confidence, not exactly. So let's say if your confidence is only, let's say it's the upper tail problem, okay? So if this is your confidence region or confidence interval, then alpha is, this is where your CI is, okay? Then the rest of this part is called alpha, right?
Or it's 1 minus, yeah?
Yeah, very good. But 1 was only based because the overall area is 1, right? So alpha is nothing but this region. And it is also called the rejection region. The green area is called acceptance region. And this blue area is called rejection region. Okay. Now remember, I have used the word region, so it's basically area. So alpha itself is area, and this one is also the area. So my question is, if a new mu comes, mu let's represent by some other color altogether, new mu, and if you could find its area from here till infinity or whatever upper tail or lower tail problem it is, you can get this p-value. So what we are saying is if p-value is less than alpha, you can reject y, or even equal to actually. You can reject null hypothesis. Why we are saying this? Come on, anyone?
Because this is to the rejection reason.
Sorry, there is some noise in when you are speaking. So can maybe someone else also try? Because there is like too much noise when you are saying something.
Probability p-value is less.
So why are you rejecting it? That's my question.
Because p-value is less than alpha, so there is no way that it will be an accepted region.
Yeah, the idea is very simple, right? If it's an area problem, area can be either 0 or positive, right? Area cannot be negative. Understood? So what we are playing here at is that if this is the acceptance area, okay, and this was the rejection area, sorry, this alpha part. So to be in the acceptance area, you have to be greater than the alpha, right? Not lesser than the alpha. Because if you are lesser than the alpha value, you will lie somewhere here, or this side. You want it to be here at least, or somewhere inside. But if you are less than alpha, how can you be inside? Again, remember, p-value is the area, so it cannot be negative. Neither can be alpha, neither the rest of the region. Any kind of integration that you are doing, you are gonna get either 0 or a positive value itself. Is it clear, or is there still a problem?
It's clear. Yeah.
Okay. Don't worry, I will give you a couple of more examples to make it very clear. Okay. Now let me ask you, how will you get this p-value?
Can we get it based on Z distribution?
Very good, very good. Z distribution is the simplest answer. Because if you remember the tables that I showed you yesterday, basically they were showing the same stuff, right? So yeah, wait. They were showing the area itself, isn't it? So what my plan here is, let's say this is alpha. This region, this shaded region is alpha. The rest of the area till infinity is normal confidence interval. Now you come up with a new mu. Let's say mu value is. Let's say mu lands here. It's a new one. So say area calculation will be done from negative infinity till this point. Okay. If it is in positive, it will be done in a reverse way. Okay. Now you just have to tell me this is mu naught. Would this mu, okay, so would this lead to rejection of mu naught, yes or no? And if yes, how would you calculate it? So basically that Z distribution is basically your Z score calculation itself. Okay. There's nothing very different about it. So let's take example so that we understand this. Okay. Now these are just guidelines. Okay. These might not be true in all the conditions. If your value is less than 0.1, then overwhelming evidence to conclude HA is true. Okay. So if you have taken 99% or something like that, still it is going out of that reason, then it is overwhelming evidence that you have HA is true. If it is between 0.01 and 0.05, means from 95 to 99% confidence interval, still it is going out, is still very strong evidence. 0.05 and 0.1, usually between 90 to 95%, it is weak evidence, but still in a lot of cases that gets accepted. Anything greater than 0.1, that is less than 90%, is not something insufficient. Means what it means is, and this figure might help you out. Anything greater than 0.1 is problematic, okay? Because when you are taking anything less than 90%, you are decreasing the range way too much, okay? And over there, p-value or any aberrance in calculating the mu will lead to the rejection of H naught, and we might just cause a type 1 error. Okay. So how do you get the p-value? It's nothing. It's literally you get the z value over there. Let's say z is 1.46, and looking in the chart, sorry, looking in this chart, let's say 1.6 or something, you look for the values of 1.6, and basically you can calculate the exact value of the area that is given there. And you have to just make sure that if it is less than alpha, then you will have to reject it. Okay. So let's say your z alpha is 1.28, but your z value or the p value that for a new mu 1.46, and when you calculate this area, that is 0.72. Okay, so this is less than 0.1. So you will have to dissect. Now, how will you calculate z value? This is very simple. You take your mean by the standard L, or whatever the new mu. Sorry, you can also use the new mu, standard FY. This will give you the sampling distribution z value. Okay, based on this z value, you can and same for the positive one as well, the upper tail as well. So once you determine the z value or z coefficient 2.29, you know how to search, right? For 2.29, what would be the answer? 2.2, and you have to go till 9890. So you have to see if it is less than 0.1, and which is it is. Okay. So that's how basically we calculate the values, and we understand, do we have to dissect or we don't have to dissect. Okay. Okay, so let's stop here. Tomorrow, not tomorrow. Okay, guys, just letting you know, although I'm available tomorrow, so if majority of you guys are in accordance, or if you guys want to attend this one tomorrow as well, I will be available. Else we can do it on Monday morning. Okay, so I will put this on WhatsApp. If everyone agrees, then only we will have the class. Otherwise, we will have the next class on Monday. Okay. I will upload this hypothesis testing PDF as well today itself. So it would be a good idea if you start going through this one by one. And with the next class, hopefully we will be able to finish this one as well. Okay. So in the next one, we will take a couple of examples to solve and see, can we reject or can we not reject the null hypothesis in our given problems. Is it clear?
Yeah.
Okay. So, okay, let's finish up the session for today.
Yeah. Thank you.
Okay. Okay, guys, so finishing up the session for today, and I will upload this one on your drive as well. So you can at least go through it. And if you want to have the class tomorrow morning, I'm available. We can do it tomorrow. Otherwise, we will do it on Monday. Okay.
Because I have class tomorrow as well, so.
Even I have to.
Yeah. Does it conflicts with this timing itself, I guess?
Yes.
Yeah, it's same time.
Okay. No problem. No problem. We will see. We will see. Otherwise, we will just do it on Monday. No problem.
Okay.
Okay, guys. See you in the next class. Bye bye.
Thank
Take
you.
care.